Hi, welcome back to McClatchy Maths. My name is Natalie McClatchy and today we are on our fourth video in our quadratic series and we're looking at completing the square. Now before we go into this video, I want to tell you how you can engage further with us here at McClatchy Maths. Firstly, you could like and subscribe and hit the notifications bell so you'll know when video 5 is available. You could share the video either on your class number note or by hitting that little arrow button to share it with a friend or family member. Why not consider telling us in the comments if you found the video helpful, and you could say thank you in a meaningful way by hitting that little love heart button and donating $2 with your PayPal account. Okay, now before we get into the video, I also want to let you know some prerequisite knowledge that you need before you can complete the square. You need to know your rules for difference of perfect squares. That's from advanced algebra. You also need to know how to factorize monic and non-monic quadratics. Okay, so we'll get started with looking at the perfect square. So previous videos, we found that the perfect square was in this form. A letter plus a variable, all squared, would expand in this way. X squared plus 2, lots of these two numbers multiplied by each other, and then plus a squared. So another quick way of saying that would be first term squared plus this times 2 plus this term squared. So using some things that we've talked about, n plus 5 all squared means n plus 5 times n plus 5. When we use FOIL to expand that, we get m squared plus 10n plus 25. 5 plus 5 makes 10, 5 squared makes 25. Okay, so let's assume that you know all of this. This is going to come in handy for completing the square. So going backwards, when we've got x squared plus 6x plus 9, we can check it's a perfect square. The way we do that is we halve that middle number and then we square it. And if there's a match, we know it's a perfect square. And then half of that middle number becomes the term, okay, that goes into this bracket. So here we go, half of b is what goes into those brackets. And then we take half of b and we square it. So what I'm going to do is consider this with 8 squared plus m. We're going to think about what number would I need to stick on the end to make a perfect square. So this is going to be my algebraic form for this. So if I think about this, half of 8 is 4. 4 squared makes 16. So the missing number here will be 16, or 4 squared. So b is equal to 8, half of b makes 4, 4 squared. So remember we said that would make 16? There we go, we've got 16. And now to factorise it, I'm going to factorise that to m plus 4 all squared. So quick way of saying that is if I want to complete this into a perfect square, halve it, square it, and then half of this is what goes in the brackets. Sometimes we end up with expressions though where they aren't perfect squares. And we're told to factorise it, and we've tried the monic quadratic method, we've tried the non-monic quadratic method, and it just doesn't work. So here's an example here. I've got j squared plus 8j plus 5. Now if I halve this, I get 4, as we just saw before, and I square it, I get 16, not 5. So we know it's not a perfect square. And if I try my monic quadratic way of factorising, remember I'm looking for factor pairs of this number that add to this number. Well, there's only one pair of factors there that is equal to 5, which is 5 and 1. 5 plus 1 makes 6, not 8. So this is my problem here. What I need to do to make this into a perfect square is add 8 over 2 squared, the 16 we just talked about. But if I add 16 and then I factorise that part, I'm not going to end up with the same expression. We're looking for equivalent expressions. So what we're going to do is if we add 16, we have to take 16 away as well, because 16, take away 16 makes 0. So we're going to add 16 for the purposes of factorising, but then we have to take it away at the end. Okay, here's example 2. Factorise x squared plus 2x plus 1. Now I can see straight away it's not a perfect square because half of 2 makes 1. If I square 1 and put it on the end, then it should be a 1, not an 8. And I can also see it's not a monic quadratic. Factor pairs of 8 include 8 and 1, which add together to make 9. No. Factor pairs of 8, 4 and 2 add together to make 6. So it's not a monic quadratic either. So I can't use those principles, so I'm going to complete the square. So what I mean by that is I'm going to use this rule here, and I'm going to be focusing on b. Half of b is 2 divided by 2, and that's going to be squared. So if I add that into the expression, then I'll be able to make a perfect square out of this part. But I can't just add something in. I've got to take it away as well so that the net result is still what I started with, because this take away this will be 0. Okay, so this will become a bit clearer as we go. So if I look here, half of 2 is 1. 1 squared makes 1. So now I've got this part of an expression, and then I've got the 1 here as well, plus 8. Okay, so if I do 1 take away 1, I'm still going to have the original thing. So I haven't changed the expression. I've just added this little part here. Now what I'm going to do is factorize this part into a perfect square. It'll be x plus 1 all squared. Negative 1 plus 8 makes positive 7. And I've done the best I can do with this one. I can't factorize that any further. Okay, let's have a look at this one here. J squared plus 8j plus 5. Once again, not a perfect square, and also not a monic quadratic as well, just by inspection. So let's use our rule here. So we're going to go with half of 8, again, squared. Take away the same thing, we'll have 5 on the end. Okay, half of 8 is 4. 4 squared makes 16. We've got the 16 again, so see here, 16 take away 16 is 0. That's what we should end up when we expand those out. Plus 5, let's put this into brackets now. It's a perfect square of j plus 4. And we're going to do negative 16 plus 5 means take away 11. Now, this is interesting because now I've got a negative in the middle and I've got a squared number at the beginning. I could consider that this is the difference of 2 squareds if I consider 11 to be in the form of a surd. Root 11 all squared means that the 11 and the squared is going to take away. So I could classify this as a squared number. So I'm going to put that in brackets as root 11 all squared, because you'll notice, cancel, cancel, I get 11. So this is where some of your surds knowledge is going to come into play. If you're not really good with surds, we've got a whole playlist on that. You could go and watch that. So now I've got a squared number, take away another squared number. I've got difference of 2 squares. So that means this plus root 11 in brackets, this take away root 11 in brackets. A little bit different, a little bit more complex, isn't it? But it's now fully factorized. I bet you never thought that was going to happen. Well, that's all we've got time for in this video today. We're just showing you the preliminary basics before we move on to some more advanced stuff. I hope you found it really helpful. If you've got any questions or would like some more practice with questions like example 3, mcclutchymaths@yahoo.com is the place to reach me, although I'm sure your teacher's probably got lots for you as well. Well, you've been watching McClutchy Maths. Stay tuned for our next video. Have a wonderful day.